look at another example. And this example is going to involve similar triangles. So streetlights mounted at the top of a 15-foot tall pole, blue line along the y-axis. A man 6 feet tall walks away from the pole with a speed of 5 feet per second along a straight path. So this little blue line segment's the man. And that segment is 6 feet tall. That's not changing. And it's moving to the right at 5 feet per second. How fast is the tip of his shadow moving when he's 40 feet from the pole? So the tip of his shadow would be the tip of that big triangle that's being formed by these black dots. So draw a picture of the situation as step one. Label things. So I've labeled the man, the height of that blue segment 6. The rate is 5 feet per second. And I've labeled the man's position from the light as the distance x, and the length of the position that the tip of a shadow is, the distance is, the tip of the shadow is from the light by d. So here is the distance that the tip of a shadow is from the light pole, and here's the distance x that the man is from the light pole. So we can use similar triangles to find a relationship between d and x. So remember, the ratio of the sides is going to be the same. So d over 15 is going to be equal to d minus x over 6. So there's my relationship that I'm going to differentiate, and differentiating both sides implicitly, I have an expression, I end up with an expression in dd dt and dx dt. So dx dt is the rate at which he's walking, right? The rate at which his distance is changing from the light pole to the man. And we want to find dd dt. So step 4, we figure out what's known and unknown and what we want. So we want dd dt. And we know that dx dt is 5 feet per second. So plugging those in, combining step 4 and step 5, gives me 25 thirds feet per second. So I am substituting with this dx dt, I'm substituting the value that I'm given, 5 feet per second, and I get 25 thirds feet per second. So that's the rate at which the tip of his shadow is moving when he's 40 feet from the pole. So that's the rate at which this long side is moving, not the rate at which the shadow is elongating. So if instead we'd set it up another way, if s is the length of my shadow, x plus s over 15 equals s over 6, then that's going to give me ds dt, meaning how long, the rate at which the shadow is lengthening. That's not the same thing as what they're asking for, which is the rate at which the tip of a shadow is moving from the light. But if we do solve this, we find that the shadow's lengthening at a rate of 10 thirds feet per second. And his rate of 5 feet per second plus that lengthening shadow's rate of 10 thirds feet per second does add up to the length, the rate of which the tip of the shadow is moving from the light. And now this last example says if the minute hand of a clock has length r, find the rate at which it sweeps out area as a function of r. So this time t is not our independent variable, r is. We want to find the rate at which the area moves, but instead of expressing something in terms of t, we're going to be expressing it in terms of r, though t still, is in the picture because things are moving relative to time. So if you draw a picture of the situation, what you're thinking of is the area of the segment of a circle and how that's changing as the minute hand moves along the circle. So remember the area of the sector of a circle with central angle theta. The area is theta over 2 r squared. So if you think about this is a generalization of the area of a circle, which is pi r squared. And of course the central angle of a circle is 2 pi. So there's our relationship. There's step 2. Step 3, we want to differentiate our relationship. So again, we are differentiating with respect to t, though our ultimate goal is an expression in terms of r. So dA dt is going to be given by d theta dt times r squared over 2, because our variable in this case is theta. Theta is what's changing with respect to time, not r. If you think about it, the length of a minute hand on a clock is not changing. It's constant. So now we need to figure out what d theta dt is. So if you think about it, the minute hand makes one full revolution around the clock, so that's goes through an angle of 2 pi radians in an hour, and there's 60 minutes in an hour. So d theta dt is 2 pi radians over 60 minutes, or pi over 30. So step 5, we're going to plug in pi over 30 into our differentiated expression. So dA dt is going to be 1/2 times pi over 30 times r squared, which gives me pi r squared over 60 centimeters squared per minute, or simply pi r squared centimeters squared per hour. So in summary, remember this 5-step process to help you. Of course, step number 2 and sometimes step number 4 are often the trickiest.